Welcome back, my friends. Today we're going to be talking about odd and even functions. And we have this nice little assignment here, and we're just going to assume that there's a function for each of these. So just assume with me that the function is like this, f of x equals this. And so real quick, what an odd and even function is that an odd function, when you flip the input negative, in other words, if you do the opposite of what you would initially plug in, you will make the output also be the opposite. You will flip the output, the sign of the output. Whereas if you have an even function, if you flip the input, if you do the opposite input, then you will not affect the output. You will still get the same output as if you had just put in a regular x, or same as the original. And then neither is, as the name implies, if neither one of those things happens. In one sense, most functions are neither, and actually the odd and even ones are special cases. And then I also told you guys, I don't know where I'm going to fit this, but that odd functions have 180 degrees rotational symmetry about the origin. I'll type that there for you somehow. I hope you don't mind. I'll put it where we can see it better. So that's for the odd functions. And then the even functions have a reflective symmetry. They're symmetrical across the y-axis. Symmetrical across the y-axis on a reflection. And that's the graphical property of the even functions. And then the neither, as the name implies, is neither. So when we get into these problems, let's start with the first one here. We have f of x equals x cubed minus x plus 1. This is neither. And the reason why it's neither, and the way you can tell by just looking at the algebra, now you could graph this and you'd see for yourself it does not have rotational symmetry or reflective symmetry. But I can tell by the algebra, and I want you to know how to tell by the algebra. And for that, I will point out that this here is an odd function. And so that is fine. That would be odd. This is also an odd function. It has an exponent of 1. And so any variable with a simple variable with an exponent is odd or even, just depending if the exponent is odd or even. But constants are even functions. And we had that nice little joke yesterday where I said, now that we're in this class, 1 is now even. Oh, I still love that joke. That's great. Yes, and the reason why it's even is because if you were to graph y equals 1, that would be a flat line. And it would be a flat line that would have reflective symmetry across the y-axis. And so you can tell that it is even. Another way to think about it is that it's 1 times x to the 0. And if the exponent is even, well, that makes it an even function. So therefore, this is an even function. And if you mix odd and even together, it's no longer, it's not like it's not binary between odd and even. It's the possibility is that it's actually neither one. And if you mix them, it's neither one. Okay, it's either only purely odd or purely even. Otherwise, it's neither. And so, as you can hopefully tell from this next one, both of them are even. And because both of them are even, this is an even function. The other way to tell is that you say, hey, I know what this looks like. This is a parabola that's shifted up 1 unit. And if you look at the graph of that, you'll realize, hey, that is symmetrical across the y-axis. That's a horrible parabola. That's way too wide. But, you get my point. It's symmetrical. That's the point. And so, therefore, it is, in fact, even. And many of us yesterday said, well, if that one is exponent 2, then this next one must also be even, right? But it's not. It's neither. Because if you graph it, you know that this is a probability shifted 1 unit left, so it loses its symmetry. It's no longer symmetrical. So if you want to think of it graphically. Now, why it seems like it should be even, right? Even exponent. Well, actually, if you do this out, don't you get x squared plus 2x plus 1? And now we have two elements that are even. We have the x squared and the 1 part that are even, and the 2x is an odd function, and because it's a mixture of things, it is neither. And we can keep going like that. I want to show you another method, and I'm going to show you on some of these other ones here another method to do this. And the other method I suggested you do is you plug in a number and its opposite number. And if it, and be careful now, please listen carefully. If doing the opposite flips the output exactly negative, exactly the opposite, I should say, then it was odd. If I plug in the opposite input and I get the exact same output as before, then it was even. The third option is that it's some other number, not the same output as before. So let me show you what I mean. So for example here, I said let's plug in 3. Okay, we're going to plug in 3, and we're going to get 3 to the 4th power times 3 plus 2. And we're going to get a number. We're going to get a numerical answer, and that's going to be 81 times 5, which I do believe is 405. So great, we get 405. That tells me nothing. Now let's plug in negative 3. And there's 3 possibilities. Either we get positive 405, in which case the answer would be that the function is even. Or we could get negative 405, in which case I would say that the function is odd. Or we'd get some other number. In that case, that would tell me it's neither. So let's plug in negative 3. What do we get? Negative 3 to the 4th power. And then that times negative 3 plus 2. And I hope you agree that that will give you 81 times negative 1. All right, times negative 1. And that is negative 81. And that is not 405. And it's also not negative 405. And therefore, the answer is neither. This one is neither. You could also multiply it out and say, look, it's x to the 5th plus 2x to the 4th and 1. Let me actually show you, and so you can actually visualize it. Whoops, x to the 5th plus 2x to the 4th. And you can now see, hopefully, that you have a mixture of odd and even elements. The even one is this, and the odd one, the odd function, is this. And so because you have a mixture of odd and even functions, this is neither. The fifth one, do we have time for this? I hope we have time. Which method would you want? Well, I can just look at algebraically. I feel like it's the quickest way. This is even, this is even, this is even, it's even. And again, I mean even degreed terms of a polynomial. That's what makes it even. And this next one here is clearly odd because both exponents are odd. So not as much work required. I mean, you could plug in 3 and negative 3. It's a very concrete way of checking it because sometimes the abstract concept is difficult to grasp. And so if I could just tell you, hey, plug in 3 and then plug in negative 3, and then you have three possibilities. Same number, opposite number, or something different. And then you know which one it is. So the nice thing about plugging in numbers is that you do have a very concrete way of doing it. This is more abstract. You have a question? Yes. Yes.
You said that was odd, right?
Yeah.
So you skipped the negative 2x?
I did say it was odd. Negative 2 coefficients won't matter. So if I have like 2x cubed, isn't that just a skinnier cubic function? It's still an odd function, right? So the coefficient's not going to matter. That was an excellent question. Thank you. Yeah. So 2x cubed is still odd. This part right here is still odd. I assumed that was no, but I should not have assumed that. So thank you for clarifying. In the same way that this 3 here is even, but Mr. Schellenberg, it's not even at all. Well, it is because it's times x to the 0 power. And that's what we're actually talking about. Well, I mean, there's another way. There's a better way to define it, but in one sense you can say that. So, and then in one sense you can say, well, the exponent is even, so therefore it's an even term, even function. Okay, so then the last ones, we just have a couple more minutes. I'm aware of the clock. Let's move on. So this one right here is not symmetrical. I'm just going to go off symmetry. This is not symmetrical, nor does it have rotational symmetry. It misses the origin, so therefore this is neither. This one here is clearly even because it has the reflective symmetry. This one is also even. It has the reflective symmetry. This is odd. It goes through the origin and has the rotational symmetry. Same thing with this one right here. This is a classic example of neither. There's no symmetry of any kind. This one here has rotational symmetry, so this one is odd. This one here is reflective symmetry, so it is even. This one is odd because it has the rotational symmetry, reflective symmetry, rotational, reflective, right? So like cosine waves are even functions, whereas sine waves are not. This one here is like a cubic, so this one is odd, or maybe not a cubic, maybe 5th power, I don't know. And then this one here is even. And that concludes our thing. I hope you learned something. This is what the quiz is about. Thank you very much. Please like, share, and subscribe to catch all our wonderful YouTube videos and possibly songs. Thank you very much. Have a good day. Buy our merch.